Materials have always played a crucial role in what human beings can do. Now, a new class of synthetic material is increasingly opening up exciting possibilities. These are the composites. Some have the spectacular advantage of being stronger than almost any other type of material and also a lot less dense, so we've been able to invent sports such as windsurfing. They're also replacing traditional materials in cars, boats and aircraft. Now, composites are mixtures of materials where one is used to reinforce the other, and they've been invented because of the limitations in homogeneous materials. Metals, for instance, are very tough, but they tend to be dense and hence heavy. In lighter strips, of course, they're easily deformed. Ceramics, on the other hand, are resistant to chemical attack, but they tend to be very brittle. Plastics are light, but they are also weak, and I can demonstrate that. I'll show you this piece of Perspex, put under tension with a small weight, and then heated quite fiercely using this paint stripper. And you'll see that after just a few seconds, it begins to bend and flexes down completely. There we are. Now, other plastics are almost as brittle as the glass. And if I hit this resin sufficiently hard with the hammer, it shatters everywhere. So who would have thought that by combining glass, albeit in a different form, with this resin, we could come up with a composite which is both incredibly tough and remarkably strong. Composites are therefore a way of combining materials that select their good features and eliminate their weaknesses. So by using glass in fibres and not in sheets when it's very weak, and by mixing it with the resin when it's a liquid and then curing it, we can come up with this composite, which is remarkably versatile. It's glass-reinforced plastic, fiberglass, or GRP for short. This is how the hulls of most small boats are made nowadays. Sheets of woven or chopped fibres of glass are first laid down and then impregnated with liquid resin. Now, this may seem a very low-tech process, but once it's set, it produces that strong, light, tough material much on display in every marina. Typically, composites are made with fibres of one material embedded in the matrix of another. In this instance, it's glass fibres in a polymer matrix. Another example is reinforced concrete. It has a matrix of concrete, which is largely sand and cement, reinforced with steel wires or bars. The matrix is weak in tension, but strong in compression, but the steel cables are very strong in tension. As a composite, this forms a relatively cheap, tough building material that can be used in large structures. Some composites are formed by mixing particles of one material in another. This paste, a preformed composite, is used to fill a patient's tooth. It's then set with light. Most modern structural composites are made from very fine fibres held in a polymer matrix. The shaft of this golf club is made from carbon fibre, which is much lighter than the traditional wood or steel, and that means that the weight saving can be put into the head, and that means that golfers can hit the ball a lot further. Not in my case, though. The strength of a composite lies in its fibres, and this is because fibres can be made with many fewer imperfections than larger pieces of material. Now, when we draw this glass into a fibre, it becomes very strong. And consequently, we can bend it into an arc which is under a lot of stress. However, if I reintroduce an imperfection by touching the top of it, it breaks almost immediately. one of the main functions of the matrix is to protect the fibres. This is ice, and when it breaks, it does so instantaneously and quite catastrophically. I'll show you that again with this hammer. This, on the other hand, is some ice with fibres embedded in it. And in this case, there's cotton wool embedded in the ice. And if I strike this with about the same amount of force using the hammer, you can see that it's much stronger. And in fact, it requires quite a hefty knock to get it to break. Now, if I gently pull the two pieces apart, you can see the fibres in between. The toughness of a material is its ability to resist cracking, which is why many composites are tough. A defect in a brittle material will go straight through, but fibres will restrain a developing crack by bridging it and forcing it to take a very circuitous route. This is why fibres, even of brittle materials, can make tough composites. The matrix plays its part by keeping the fibres separate and aligned in the required directions. Unlike most homogeneous materials whose strengths lay roughly the same in all directions, the strength of a composite lies in the direction of its fibres. And in the case of a natural composite, such as wood, that means in the direction of its grain. Now, wood is a composite made up of cellulose fibres embedded in a matrix of something called lignin, which is a type of resin. And whilst it's actually quite strong in this direction, it's very weak in this direction. And to increase its strength, one would have to bond these fibres in opposite directions, like this. But of course, someone's already thought of that. Plywood. Another way of achieving strength in different directions is by the appropriate weaving of the fibres before the matrix is added. With 3D weaving, whole engineering structures can be pre-formed. This pre-woven structure is the basis of a nose cone of a Tornado fighter plane. By careful arrangement of its fibre layers and the use of very special resins, the nose cone can be made radar transparent, an important advantage in this type of aircraft. An advantage of composites is that you can very often make the material and the product in a single operation, just as a tree does by growing both its wood and its structure simultaneously. It happens in filament winding. A stiff aramid fibre is first passed through a bath of resin, the matrix. It is then wound round the required shape. In this case, the product and the material are created together. With computer-aided design and manufacture, it is also possible to lay down the fibres so as to meet the stresses the product will be subjected to. In this way, the necessary strength is achieved with the least amount of materials and energy, and waste is virtually eliminated. The so-called advanced composites, that's those made with stiff fibres, really began in the mid-1960s with the development of carbon fibre. Now, this material found immediate uses in sporting goods and in particular in fishing rods. And here's a very light carbon fibre rod with an equally light carbon fibre reel. And if they hadn't found these uses, the development of the material may have stopped there and then. Modern carbon fibre is 6 times stronger than the equivalent weight steel. And here's a piece of steel which weighs the same, and you can see that it's altogether more flexible. In fact, for us to produce a piece of steel that's as strong as this, we'd need this piece. It's 16 times heavier and 4 times thicker. Now, carbon fibre is made relatively easily from an acrylic polymer fibre such as this, and through a 2-stage reaction, the first of which carried out at about 200 Celsius, the sort of thing you could do in your oven at home, but in an oxidizing atmosphere, produces this material. The second, or carbonisation reaction, requires a much higher temperature, in fact temperatures of over 1000 Celsius, and no oxygen at all. And that gives us the final product, true carbon fibre. Now, the main applications for carbon fibre composites these days can be found in the aerospace industry. Helicopter rotor blades, once metal, are now fabricated out of layers of composites, giving them a life free of fatigue. Within this composite sandwich, it is these carbon fibre sheets impregnated with epoxy resin that provide the crucial longitudinal stiffness. The assembled blade has to then be cured, heated in an oven. to allow the thermosetting resin to set and form the tough but flexible matrix of the final blade. With composites, it is possible to vary the stiffness along the blade, something not feasible in metal. This has led to huge advances in rotor blade design. Ease of manufacture means that more and more companies are using composite materials. So what are the major practical manufacturing advantages of using these materials?
Well, for a small car producer, the investment costs of producing a steel car is phenomenal, you know, with the pressed steel. I mean, we have a much lower cost method of producing cars with composite materials in terms of tooling, processing, and so on. We make our own tools in-house, so we can introduce model changes very quickly.
Now, the days of traditional laying up with rollers are over. You have pioneered a new technique here, I believe.
Yes, we have a closed mould technology which we've developed ourselves, which relies on vacuum as a clamping force. It avoids the need for steel presses. We evacuate the space, and the negative pressure generates the tonnage that we need over the surface area to provide the clamping forces.
And what about the resin material, the matrix, that's injected afterwards?
Yes, we inject a resin which is activated on its way into the tool, and that has a limited shelf life. And once it cures, we have a rigid moulding from a closed mould system.
Now, some of the moulds seem quite complex, and I know you've been pre-forming the mat before it goes in there.
Yes, we found that the most important thing for any composite is the correct placement of the fibre reinforcement, much the same as one places steel rods in concrete. So we developed our own pre-forming system, which enables us to make rigid, dry glass shapes that can be positioned very precisely inside the moulds.
Does using composites give your designers a greater scope for the shapes they can come up with?
You have more opportunity to make sculpted shapes, as opposed to designing for pressed steel, where, you know, you have much sharper corners and so on. We can get much rounder shapes, and it gives our styling people a lot more freedom to design for the materials.
Lastly, composites have a reputation for energy absorption. Do you use this for your safety considerations?
Yes, we have a different way of absorbing energy in a composite structure. In a case of a steel car, you get the progressive deformation of steel. In our structures, we have to have progressively flexible, progressing to more rigid materials on the front end, for example, to absorb the energy in a different way.
Composites are leading the way in new materials, but they tend to be quite expensive and so currently only find uses in specialist or upmarket fields, such as this nearly all carbon fibre racing bicycle soon to be produced. The framework and cladding of this wheelchair are also carbon fibre, and therefore it's a lot more durable and, of course, a lot lighter. Lastly, should it ever find its way into a guitar shop, this will be the carbon fibre guitar, not suitable for the heavy metal band. Up until now, we've been chiefly concerned with composites made from inorganic fibres in a polymer matrix. And whilst these are invaluable structural materials, it seems that the composites of the future may have matrices made from ceramics or even metals. Dr. Jones, most people associate ceramics as being very brittle. Why have we chosen these as a material to make a new composite from?
Well, the very nature of a ceramic indicates it is a brittle material which an engineer can't easily use in applications where the ceramic might come under severe mechanical load. Aerospace has driven the research programs to date. The problems in an engine are that to get increased engine efficiency, you must operate the engine at higher and higher temperature. And we're now very close to the limitations of metal turbine blades. And what we need to do now is to move into a new realm of materials which will withstand much higher temperatures. And obviously the ceramics are the materials for that application.
Tell me a bit about the manufacturing processes needed to produce these types of material.
Well, we can formulate ceramics to be glassy materials, rather like this. And a glass at elevated temperature can be turned into a liquid. So we have the properties of a fairly low viscosity liquid which we can use to infiltrate the fibres. After we've done this, we end up with a fibre-reinforced glass material, and on subsequent heat treatment in a furnace, we can turn that glass into a crystalline ceramic.
How can you ensure proper bonding between the matrix and the fibres?
The bonding is very important because you might think that we need a strong bond between the fibre and the matrix. And if you were looking for a high-strength material, this would be an important factor. But high strength does not mean high toughness. In high strength, we transmit the load from the matrix to the fibre and fully utilise the strength of the fibre. And therefore, to do that, we need a strong interfacial adhesion between the fibre and matrix. If we want high toughness, we actually want the fibre weakly bonded into the matrix, so that when the crack starts to propagate through the material, it sees a weak interface and it turns at right angles and runs along between the fibre and the matrix. And also on the last few seconds as the material starts to fail, what we want is for the fibre to break remote from the crack and for these fibres to be pulled out of each half of the matrix. We call it a shaving brush fracture. But in doing that, we're again using up fracture energy and work of fracture.
How do ceramic and metal matrix composites therefore compare?
They're very different materials. With a metal, you often have the fracture toughness that you need. It's the fracture toughness that we're trying to develop in a ceramic matrix composite. But what you don't have with metals like aluminium and aluminium alloys is a high stiffness. So fibre reinforcement of these materials has the aim of increasing the stiffness to weight ratio. So metal matrix composites are designed more to give you very high stiffness structures but at very low weight penalty. And I believe that the application areas for those materials in the near future will be in the automotive industry.
Today's advanced composites offer enormous advantages over homogeneous materials. Never before has it been possible to tailor a material to meet such specific properties. Composites can be designed to meet precise requirements in strength, exactly where it's needed, therefore saving material and, of course, saving weight. Often, cheaper fibres can be mixed with more expensive materials for a more economical outcome, but of course in Formula One racing, not much expense is spared. And this is the completed machine. And apart from the engine and the tyres, the whole thing is carbon fibre. And it's this composite's strength and its ability to absorb energy that means that drivers these days can walk away from high-speed crashes that a few years ago may have proved fatal. But perhaps no example is more dramatic than the carbon-carbon composite that makes up the nose cone of the shuttle spacecraft. This has the spectacular property that it increases its strength up to a temperature of 2,500 Celsius. Almost certainly, the revolutionary materials of the future will be composites.